Swayam Prabha. Digital India. Educated India.
So if you now look into this probability as kind of a fraction, in the denominator you would have the total number of ages, and in the numerator you would have k, right, the number of ages in the cut. So in the below thing, in the denominator, how can I now have, and mind you, this I want a lower bound on P E1. So that means I would want a lower bound on the number of ages. Now if you look into this result, so look into this result, this is true for all vertices. So take a sum over all vertices on both sides of this inequality. So summation of degree is what? Summation of degree is related to the number of ages, right? So when you sum the degrees, what do you see? Each age contributes to 2 degree sum, right? So if you sum this degree, it should be twice of the number of ages on the left side. On the right side you get n into k, you are summing over all vertices. So you straight away get twice of E is greater than equal to n of k. So n, the number of ages is bounded by nk by 2. So when I write mod C, it means the number of ages in the cut. So an implication of the above lemma is the following. Because this is k and this is greater than equals to kn by 2. So this is your nothing but so probability of this is, oh sorry, no, that should be 1 minus 2 by n, sorry, that epsilon 1 was not contracted, remember that, I am sorry. Yeah, we will plug it later on. So, an edge of the cut is contracted in the very first instance is now, you see, a very low probability, right? It is a very low probability event. As I go along, what will happen is the number of edges keep reducing, these probabilities keep increasing, but again there I would show that they are not going to increase by too much. So, as you know, this is less than equals to 2 by n, mind you, there I need, here the inequality is on this side, there I need on the other side, and mind you I had defined is not contracted. So, these things would be probability of this E1 would be greater than equals to 1 minus 2 by n, right? Do you agree to this? If you have any difficulty in understanding, just pause here a little bit and get it clear. What was this probability? An edge in the cut is contracted at the first instance, right, when I started. Right. So, this is upper bounded by 2 by n. What is my E1? Event that an edge of the cut is not contracted in iteration 1. The complement was upper bounded by 2 by n. So, this should be lower bounded by 1 minus 2 by n, that is what I meant to say. So, this is like 1 minus 2 by n. Next I need to figure out this one, but to figure out this one the graph has now changed, because after the first iteration no longer the graph is looking as nice as this, but it is something like this. Agreed? Okay. Now think of this. I had this big graph G which I am contracting, and I am at some iteration J. So look at this new graph at this iteration, right. So you have done contractions, reached to a stage. Let us call this graph G dashed. Now if I get a cut in this graph G dashed, and with this, so if I get a cut in G dash, this is a partition, right. Now if I go back to the original graph, a cut in G dashed is also a cut in G. But not the other way around. As a proof of what I said, mind you, I took a minimum cut here, went back there. So cut in here was preserved as a cut in there, right. But there is no guarantee that a cut in there will be a cut in there. By cut I mean minimum cuts, right. I will crucially use this observation that a cut in this contracted graph is also a cut in the original graph. So you have gotten to this graph G dashed after j iterations. How many nodes are in this graph? After the first iteration it was n minus 1. So after j iterations it should be fine. Okay. Mind you, my goal is now to find these conditional probabilities. So I am looking at a situation where after the jth iteration no edge of the cut has been touched or contracted. So I am in this situation to set up the conditional probability. J iterations gone by, I know now number of super nodes is n minus j and none of my cut edges has been touched till now. Keep a note, not the other way around. So every cut of G is a cut of G. Every cut of G dash is a cut of G. Now, if that be the case, then this should still hold. That if you now look into all vertices of G dash, where there are now n minus j super nodes, all of their degrees should be greater than equal to k. Otherwise, if it was less than k, then the minimum cut size of the original graph G would not have been k, it should have been something less. Agreed? Right. So because of this implication, because of this, it implies that so number of edges in G dash is at least what? Earlier what it was? K into n. Why? Because you are summing over all vertices. In this new graph, how many vertices are there? N minus j. Right? After j iterations, there are n minus j nodes remaining. So now this set V has gone to some V dashed, but the cardinality of that set V dashed is n minus j. Right? So on one side you would sum up to n minus j, right? So it would be k into n minus j by 2. So do it as a formal exercise. So let us call this set to be E dashed. Right. So I am not writing the big thing. So what should be in here? That probability that a cartridge was not touched at the jth iteration, given that the cart is still there. There was no disturbance till now. So in effect what I have done is I have got, again you see, so this was an upper bound 2 by n. For the jth iteration I have got an upper bound of 2 by n minus j. So now if you go back and plug there, for the jth step it would be 1 minus 2 by n minus j, right. Now what I suggest is, now you have got all terms, right. Just do this product and see for yourself what is coming. Now I have everything ready, all probabilities ready. This I had figured out, and each one of these intermediate steps I have figured out. Now just go through the motions, go through the calculations. I suggest you write a few terms before this last term and do this simplification. Professor, I have 10 minutes more, right? Yeah, okay. What is this coming out to? This should come out to a nice expression. See, you would get a n minus 2 in the numerator here, and you would get an n minus 2 in the denominator here. So that should cancel out. So similarly, something here should cancel out with another term there. So there would be such nice cancellations. And you'd left over and you'd be left with this. If you do this correctly, it should come to this. Yeah, and there should be a 2. So that is 1 by n choose 2. Okay. So this was the probability of success. But what I am interested, I told you is I would bound the error probability. So it is the complement event. So final result what I have got till now is so that means this, right? So I promised you that I will give you a bound on the error probability. What is the error? That my algorithm could not find the minimum cut. But you should at this point of time tell me what the hell you are doing. You know, if n is large, you are saying that with almost probability 1, you have failed, right? Because as n grows large, 1 by n choose 2 goes down, and then you are saying that, well, with a probability of at most 1, anyway you will get a probability of at most 1, with the probability of at most 1, you have failed. So what the hell have you done? Now herein comes a trick of randomized algorithm for algorithms that has a one-sided error. Mind you, for a minimum cut, you could not find a cut that is less than the minimum cut, right? So if you had erred, the cut size would obviously be greater than the min cut. You agree to this? So this algorithm has one-sided error. If this algorithm has one-sided error, we can do something now better. What I would now do is, I will make, so this was my, so now think of the algorithm that I have designed for you as one black box, right? What I would do is, I would run multiple instantiations of the same algorithm, right, but independent to one another. So that means for your first box, for your first run, there was a sequence of contractions which was a random choice. In your second run, you will again make random choices. These two sequences should not be the same with high probability. You keep doing this, right, and take the minimum out of them. Now mind you, now your error probability was, for one run it was 1 minus 1 by n choose 2. If you run it second time, your error would come to, it would now be a product, because these are now independent events, right. So 1 minus 1 by n choose 2 into 2. But if you are now going to run it multiple number of times, say n choose times, what is 1 minus 1 by x whole to the power of x? That gets you close to e to the power of minus 1, right. So what I do is, I now run it for n choose 2 times. My error probability would come down to e to the power of minus 1. If you run it more, you can even bring down the error probability. So for algorithms that has a one-sided error, you can do this. This is known as boosting the, well, you might say the error or the success. So if I say boosting the error probability, it means pushing the error probability down, and if I say the boosting the success probability means, right. So in here, boosting the error probability meant that I wanted to keep it down. So what I did was, I looked at the quantity and you can figure out so this tells us that I mean, I should be a bit. So what was the idea? This was one instance which had an error probability of 1 minus 1 by n choose 2. What I did was, I kept running it multiple times. How many? N choose 2 times. Now obviously this comes with a cost. Your time complexity has gone up, right? So what time did one run of your algorithm take? Kind of what you did was, figured out, picked an edge uniformly at random, collapsed all edges that were incident to it. So for one if you look at one contraction, you might take at most linear time, right? Because if you are contracting an edge whose one of the end vertices has a high degree, so has almost edges to everything, then you might end up taking linear for one contraction. You are doing n minus 2 contractions. So each run might take order n square, right? And n choose 2 is roughly order n square, right? Because it's n into n minus 1, the dominant term is n square. Now you have to choose what makes you happy. You give less time, your error probability is high. You give more time, you can bring down your error probability. Now that's your choice as a designer, what you would do. So you can do this exercise that what if, say, instead of running n choose 2 times, say I run n choose 2 log n times and see what happens to the error probability. So the more number of instances you would run, your error probability would keep coming down. Mind you, it's because your algorithm has a one-sided error. If it was having results on both sides, this would not have worked. Now mind you, when you studied the algorithms which Venkatesh taught you, which were kind of those Las Vegas algorithms, your time was a random variable, right? And he showed expectation on the time taken for quick sort, for quick select, so on and so forth. Here the algorithm time has no randomization component to it, because I do n minus 2 iterations and I then contract whatever I like. So the time analysis, the time complexity analysis is a deterministic analysis, but the error thing is a probabilistic. So the algorithm is probabilistic, but the time complexity is not going to be a random variable here. Fine. So this is a Monte Carlo algorithm. As I said, you are allowed to make errors, but you want to put a probabilistic bound on the error.